Hello and welcome to this course titled RF and Microwave Engineering, having course code EC701. This course is made for BTech undergraduate student for Electronics and Communication Engineering. Myself, Dr. Aveli Banerjee, Assistant Professor of ECE Department, Guru Nanak Institute of Technology. This is my email ID. If you have any queries, you can send an email to this ID. So we have started with module 2. We have completed this section, that is high frequency circuit elements. Then we have started the next section also, that is waveguide passive components and their S matrix representation. There we have seen some microwave passive components also. We have seen attenuators, phase shifters, then we have seen the magic T, then circulators, and now here we will start with the remaining microwave passive components. So after completing this module 2, the students will be able to learn the scattering matrix for microwave passive components, and they will be able to develop fundamental understanding of the two-port RF network and matching techniques. So on completion of these module, the student will be able to have the basic understanding of the two-port network and the scattering matrix for the different microwave passive components. So the course outcome will be COEC 701.2 and COEC 701.3. So these two are the course outcomes after completing this topic or this module. So in the previous lectures of this module, we have completed, particularly talking about the next section, the later section of the module 2. We have covered the transmission matrix, their relationship. Then we have seen microwave passive components and their S matrix representation. Particularly, we have seen the attenuators, phase shifters. Then we have seen waveguide Ts. Then we have studied about magic T, and in the last lecture we have gone through the circulator. There we have studied the different type of circulators. The different types were 3-port circulator, 4-port circulator, and microstrip circulator. Now in this lecture we are going to study isolator and directional coupler. Now here coming to an isolator. So an isolator is a two-port non-reciprocal device which produces a minimum attenuation of wave propagation in one direction and high attenuation in the opposite direction. Thus, when inserted between a signal source and load, almost all the signal power can be transmitted to the load, and any reflected power from the load is not fed back to the generator output port, which eliminates the variations of source power output and frequency pulling due to changing loads. So an isolator can be constructed in a rectangular waveguide having dimension A cross B. Now already we have seen the rectangular waveguide. So here this is the A dimension and this is the B dimension of a rectangular waveguide. So here the operating dominant mode, which is shown here, this is the operating dominant mode. The non-reciprocal characteristics are obtained by establishing a steady magnetic field, that is H0, placing H0 in the Y direction and placing ferrite slab at any of the longitudinal planes, that is x is equal to x1. So this is shown in the figure. So here near and parallel to the narrow waveguide wall where the magnetic field exhibits circular polarization. So this occurs at this x1. So here x1 is equal to basically it is a by 4 or 3a by 4. So here for the propagation of waves in plus z direction, this is the wave propagating. Here I have shown the direction. This is the z, this is y, and this is x. So this is the propagation of the waves in x plus z direction. The direction of the rotation of h in the planes at x1. This is the x1 position is equal to a. This is a dimension of rectangular waveguide, a by 4. This x1 is located at a by 4, and 3a by 4 are opposite to each other. The non-reciprocal characteristics is achieved by placing a ferrite slab. Here we are placing a ferrite slab at any one of these two planes. The required steady state magnetic field, that is the H0, already I have told that is H0 in the y direction. So this is the y direction. Is established by placing permanent magnetic poles between the two broad walls. So here this is the basic construction of the waveguide isolator. So these are the ferrite slab, and this is the structure, how it forms in isolator. Now it is known that the attenuation in ferrite for negative or clockwise circular polarization is very small, whereas for positive or counterclockwise circular polarization is very large and near the resonance frequency. Here resonance frequency we will assign it as F0. Now therefore the ferrite slab is placed in such a way that while transmission it encounters negative circular polarization in the reverse direction. The steady magnetic field is said to be equal to the resonant value. The isolation of the order of having 20 to 30 dB in the backward direction and a transmission loss of 0.5 dB in the forward direction can be achieved. So here the VSWR is in the order of 1.1. Since the reverse power is absorbed in the ferrite and dissipated as heat, the maximum power handling capability of an isolator is limited. Now to increase the capacity of heat dissipation, two ferrite slabs of smaller heights are used, and instead of one with a larger height. So this is the basic requirement for the construction of an isolator. The requirement of a very high steady magnetic field is the main drawback of waveguide resonance isolator at higher frequency. The isolator we will study the next, that is the isolator known as Faraday rotation isolator. So here a Faraday rotation isolator is a circular waveguide section axially loaded with a ferrite rod of smaller diameter. So this is shown in the figure. This is the ferrite rod, and this is 45-degree twist here, and this is the resistive card. So this is the Faraday rotation isolator. The ferrite rod is subjected to a steady axial magnetic field H0 of strength much smaller than the resonant intensity, so that dissipative loss in ferrite is neglected. Now here the dominant mode is TE11 in the circular section can be decomposed into two oppositely rotating circularly polarized waves of equal magnitude. These waves encounter different permeabilities. Here permeability is denoted by mu. So one is denoted as mu plus and another is denoted as mu minus. So for clockwise it is mu plus, and mu dash plus, and for anti-clockwise or counterclockwise, it is denoted as mu dash minus. So for this, the direction of the that depends upon the direction of field rotation and exhibit changes in the phase velocities. So this will result in a change in the plane of polarization of the main mode, that is TE11, which will experience gradual rotation theta during propagation to the other end. So the rotation angle here, we will consider it as theta, which is proportional to the length of the ferrite rod. In this case, for the reverse wave, the direction of rotation remains the same, confirming the non-reciprocal characteristics of the ferrite. So the isolator input is a 45-degree twist where a tapered resistive card is mounted. So this is the shown in the figure. This is the tapered resistive card, that is the ferrite rod. So it is mounted here. Now this is parallel to the broad wall of the rectangular waveguide. This is the rectangular waveguide. Now the dominant TE10 mode does not get attenuated while transmission and is rotated at 45 degree at the twist output and enters the circular waveguide through rectangular to circular waveguide transition as the TE11 mode. The length of the ferrite rod is selected so as to obtain Faraday rotation, that is 45 degree. Here we have considered the theta as 45 degree at the output and regain its original polarization. The plane of polarization of the reflected wave from the load is again rotated by the same angle theta, that is 45 degrees. So there is again one rotation, that is in the 45 degree, so that the emergence through the 45 degree twist becomes aligned with the surface of the absorbing plate and gets absorbed. Thus the non-reciprocal isolation takes place. So typical insertion loss and isolation are approximately, insertion loss is approximately 1 dB and isolation is 20 to 30 dB respectively for these isolators. So for isolators are also available in the coaxial and microstrip forms. So now coming to this is the basic concept about the Faraday rotation isolator. Now, for an ideal lossless meshed isolator, the S21 will be equal to 1 and S12 will be equal to S11 will be equal to S22. So that is equal to 0. So this is the S matrix for an ideal lossless meshed isolator. Now we are trying to solve one related numerical for isolator. So in a question it is given a meshed isolator has insertion loss of 0.5 dB and an isolation of 25 dB. Now we need to find the scattering coefficient. So the insertion loss is equal to 0.5 dB according to the given data from the question. So here we know that the formula for insertion loss is equal to minus 20 log S21. So we will find out the value of S21. So it is we have obtained, that is 10 to the power minus 0.025. Now the next thing which is given is isolation. So isolation is given as 25 dB. Already I have told you that the insertion loss is approximately 1 dB and this the isolation lies between 20 to 30 dB. So here in this question, it is given as 25 dB. Now the formula for this is minus 20 log of S12. So from here, we will find out the value of S12. So it is approximately equal to 10 to the power minus 1.2. So since there is no reflection, so S11 is equal to S22 is equal to 0. So we have obtained the value of S21 and S12. So now what we will do, we will substitute the values of S21 and S12 in the S matrix, and then we will find out the scattering matrix. So already the coefficients we have obtained. So the matrix representation will be in this form. So this is the S matrix for the isolator. Now moving to the next component, that is directional coupler. Now a directional coupler is a 4-port passive device commonly used for coupling a known fraction of the microwave power to a port, that is coupled port, in the auxiliary line flowing from the input port to the output port in the main line. So the remaining port is an ideally isolated port and match terminated. There are 3 basic types of directional coupler. One is multiple aperture waveguide type. The second one is coupled coaxial or strip or microstrip line. And the third one is branch line couplers. Now this is the schematic, this is the directional coupler waveguide and strip line for the schematic diagram of these are shown here in this slide. Now here, this is the port 1, this is the port 2, this is the port 3, and this is the port 4. So this is for the strip line case. This is port 1, this is port 2, and this is port 3 and port 4. Now the theory of the waveguide coupler was first established by Bethe using a single hole in the common broad wall of 2 rectangular waveguides. Now commonly it is known as Bethe hole directional coupler. Now practical waveguide directional couplers are multi-hole couplers in which the desired coupling response versus frequency can be achieved by proper selection of the number of holes and size of the holes. This is the basic criteria for designing a directional coupler. Now the waveguide couplers are forward couplers since the coupled power in the ancillary guide flows in the same direction as the input power in the main guide. Now, whereas the coaxial strip and microstrip couplers are backward couplers because the coupled energy travels in the opposite direction of the input energy flow. So the performance of a directional couplers is measured in terms of 4 basic parameters. One is coupling, the another is transmission loss, then the third is directivity, and the fourth is the return loss. So when all the ports are matched, so this can be defined as so this is the C, that is the coupling. So it is in dB, so it is defined as 10 log P1 by P4. So this is the power at port 1 and this is at port 4. So this T is the transmission loss. So it is equal to 10 log P1 by P2, and D is the directivity. So it is equal to 10 log P4 by P3, and this R is the return loss. So it is equal to 10 log P1 by PR. So these are the performance of a directional coupler. These are the measurement of performance for a performance of a directional coupler. So this P's are the powers at the ports. So this is power at port 1, power at port 4, power at port 1, power at port 2, power at port 4, power at port 3. This is P1 and this is the radiated power. So these are the P's denotes the power. Now this is the Bethe hole coupler. So here a single hole is there. So this is waveguide directional. This consists of a single hole broad wall aperture coupled waveguide coupler, where the hole is located at the center of a common broad wall of two waveguides inclined at an angle theta. So this is the theta angle. I have defined it. So here at an offset position D. So this is in this figure, it is shown the D position now of the two parallel waveguides. Now, if the aperture is small compared to the wavelength, it can be considered as an electric dipole normal to the aperture with dipole moment proportional to the normal component of the electric field in the main guide at the aperture, plus a magnetic dipole in the plane of the aperture with dipole moment proportional to the tangential component of the exciting magnetic field at the aperture. The coupling of the auxiliary guide is due to radiation from these dipoles. So the electric dipole radiates equally in both the directions longitudinally, but the magnetic dipole radiates asymmetrically in longitudinal directions. By varying the angle theta between the two waveguides, or by adjusting the distance d, powers in port 3 and port 4 can be controlled. Ideally, power at port 4 can be 0 or isolated, whereas that at port 3 is maximum to achieve directional coupling. So for the center hole, for the center coupling hole, since practically P4 is not equal to 0, the directivity is finite. So the coupling and directivity of this Bethe hole coupler are, it is denoted by C for the coupling and for directivity D. So the formula is given here. This is for the coupling of the Bethe hole coupler, and this is the directivity for the Bethe hole coupler. So this R0 here, this R0 is the radius of the hole, and this A cross B is the waveguide cross-sectional dimension. Here we are using it, and beta is equal to 2 pi by lambda g, where lambda g is equal to lambda 0. This thing already we have studied in the rectangular waveguide section, that is in the module 1. There we have seen the different types of waveguide. One was rectangular waveguide and another was circular waveguide. There we have seen all the definition. This is the beta, this is the lambda g, wavelength, phase constant, propagation constant. Every formula and concept we have seen, and we are using here the same because here we are using the rectangular waveguide. So here the guide wall thickness is assumed negligibly small. So the optimum angle theta, this angle theta for P4 is equal to 0 is obtained from the relation cos theta is equal to lambda g square by 2 lambda square, 2 lambda 0 square. Here the guide wall thickness is assumed negligibly small. So now for offset hole, the optimum forward coupling, that is P4 is equal to 0, is obtained for the offset values D given by sine of pi d by a, that is equal to lambda 0 by root over 6a. So the maximum coupling and directivity are given by capital C is equal to 20 log of this, and the directivity is given as 20 log of 1 by capital X. So here the X is defined. So this is the coupling and directivity of the Bethe-Hall coupler. Now, for non-zero finite wall thickness, the coupling decreases and will be 1 to 2 dB less compared to the zero thickness. Now, we will see one numerical, that is design a center hole Bethe-Hall directional coupler with air-filled rectangular waveguide of dimension A and B are given 0.9 inch into 0.4 inch at 9.8 gigahertz for 20 dB coupling and 40 dB directivity respectively. Now the solution here from the question, the given data are A, B, it is given, we know the F0, that is 9.8. Then from there we will calculate the lambda 0, that is equal to C by F. That is we have obtained 3.06, this all in centimeter. We have converted this inch in centimeter. Then we have converted this 0.4 inch into centimeter, and then we have obtained the value of K0, that is equal to 2 pi by lambda 0. There we have obtained the value as 2.0533 radian per centimeter. Then we have calculated lambda g by lambda 0 from the given formula, which just we have seen, that is 1 by root over of 1 minus lambda 0 by 2a square. So here we have obtained the value of lambda 0 as 3.06. We have replaced it, and we have already in the given data the value of A is given. We have converted it into centimeter, that is 2.286. We have substituted, and then we have obtained the result as 1.3458. This is the value of lambda g by lambda 0. Then we have calculated the value of lambda g, because we know what is lambda 0, that is equal to 3.06. So ultimately we have obtained the value of lambda g as 4.118 centimeter. Now from there we have calculated beta, that is 2 pi by lambda g. Then we have calculated the cos theta, that is half of lambda g by lambda 0 square. So from there we have calculated the value of theta. So theta is obtained as 25.09 degree. Now what we have to do, we have to find out the coupling factor, that is C is equal to 20 dB, we know. So from there we have obtained the value of R0. We have substituted the value of coupling factor in this expression, and we have find out this R0. So these are the intermediate step I have shown. We have substituted all the values here, but the R0 is unknown. So from this is obtained, and from here the next step is R0. From here R0 is obtained as 0.0631. Then we have find out cube root to obtain the value of R0. After obtaining the value of R0, we have obtained the value of D. So D is equal to, we have got 1.143 centimeter. Now we have written the formula for D. So D we have substituted, and from there we have substituted the value of directivity as 40. We have substituted all the values, where beta 1 is unknown. So from these are all the intermediate steps I have shown here. So from here this lambda g1, lambda 01, lambda g1, lambda 01, I have written all these things, and from at last we have obtained the value of lambda 01, that is equal to 3.02 centimeter. Now this lambda 01 is substituted here to obtain the value of F1. So C is known. C is equal to, it is considered as 3 into 10 to the power 8 meter per second, and this is the value of 01. We have converted into the value into centimeter. So it is F1 is obtained as 9.929 gigahertz, and then we have calculated the value of F2. So it is equal to 2F0 minus F1, that is equal to 2 into 9.8 minus 9.929. So this is equal to 9.671 gigahertz. So this is the value of F1 and F2 we have obtained from all the calculations. So in this lecture, we have seen the basic schematic diagram for isolator. There we have seen the Faraday rotation isolator, how it works, how the construction of the Faraday isolator. Then we have seen the Bethe hole coupler, that is one type of directional coupler. We have seen the construction of directional coupler and how it works, and we have seen also the basic definitions of the coupling parameter, then directivity, then all the losses. We have seen here how to solve the numerical related to directional coupler. We have seen that also. So here in this lecture, we have seen only one type of directional coupler, that is Bethe hole coupler. In the next lecture, we will see the another type of directional coupler, that is the multi-hole directional coupler. Here the difference between the Bethe hole and the multi-hole is that in Bethe hole there is only a single hole is there, whereas in the multi-hole there are various there are multiple holes. So this is the basic difference between these two. So in the next lecture we will study in detail about the multi-hole directional coupler.